Hello everyone, my name is Ronggu and I'm from Meladalan University. And today I'm going to introduce the paper about verifiable and scalable mission plan synthesis for autonomous agents. So what are autonomous agents? They are systems that can move and perform different kinds of tasks fully automated, and they can perceive the environment and react based on the information that they get from the environment. So this kind of system can actually be used everywhere in our life, like robots in autonomous warehouses and vehicles in autonomous airports. But mission planning is one of the main crucial problems that remains unsolved in these kind of systems, and it includes path planning, which aims to generate a sequence of positions to visit, and task scheduling, which aims to schedule a sequence of tasks for the agent to finish. And in this presentation, I'm going to use an industrial use case called autonomous query that is provided by our industrial partner, Volvo Construction Equipment. So as you can see in this picture, in the autonomous quarry, there's an autonomous wheel loader that digs stones at the stone pile and then loads the stones into the autonomous trucks, which transfer the stones to the premier crusher where the stones are crushed into fractions. And then these trucks are gonna load the crushed stones and transfer them to the secondary crusher, which is the destination. And during this process, when their battery level is low, all these vehicles need to go to the charging point to charge themselves. So based on the requirements given by Volvo CE, we categorize them into four general categories that can be met in all kinds of autonomous agents. They are milestone matching, task sequencing, and timing requirement, which means tasks must be done within a prescribed time limit, and event reaction, which means if some tasks are triggered by events like temperature level is low event, the agent must go to charge themselves timely so that they can avoid consume all their batteries. And um, we want to design these autonomous agents in order to enable them to solve the path planning and task scheduling problem and satisfies the requirements that we mentioned before. So now I'm going to introduce the theta algorithm that we use in this study to solve the path planning problem first. So this theta algorithm is simply suitable for calculating paths in 2D maps. And briefly speaking, theta algorithm calculates the shortest path in a grid that discretizes the real environment. And the time of calculating paths for multiple agents is the sum of the computation time in each of the agents. Because we do not need to consider the overlap of the paths, and this conflict of paths is dealt with by collision avoidance algorithms when the agents actually starts to move. But now we are just making the mission plans. And also there are some difficulties in task scheduling, like the the execution time of tasks is uncertain. It's between BCET, which means best case execution time, and WCET, which means worst case execution time. And also because of the uncertain execution time of tasks, the movement of agent also causes uncertain time. So for example, in this picture, if agent 1 wants to go to milestone B and C, it has to wait because these two milestones are occupied by agent 2 and 3 respectively. So it has to wait until all of them finish their, or one of them finishes their task, and the task execution time is uncertain. So, and the other aspect or difficulty of task scheduling is about scalability. Because task scheduling is NP hard, and when the number of agents is too many or the number of tasks and positions in the environment is too many, it's simply impossible to build the model manually and synthesize mission plans automatically. In our previous work, we proposed a method and a tool called TAMA for model generation. But based on our experiments, this tool is only limited to synthesize mission plans for less than 5 agents. So if the number of agents is too many, this tool runs out of memory and never generates any result. So in this presentation, I'm going to introduce a new method to solve this problem. But before that, we need to know some preliminaries of this method. Since the model that is used in this new method is actually based on the original model of TAMA, we need to introduce them a little bit. So there are 3 kinds of TA models. TA is short for time automata that models the behavior of agents, and 2 of them are shown in this slide. So picture 1 shows a part of the movement TA, which models the movement from milestone PA to milestone PB, and the movement time is at least TT01 time unit. And picture B, or picture 2, shows a part of the task execution TA, which models the idle state of the agent, and the execution of task named T1. When all these preconditions are satisfied, T1 is allowed to execute, and execution time is between the BCET and WCET of this task. And a broadcaster channel named Go is used to synchronize these 2 TA models. And another TA is called monitor, which is used to monitor the signals that is concerned by this agent, like the battery level. And the signal is modeled as a real-valued clock variable. So since we use exhaustive model checking to synthesize mission plans in TAMA, we have encountered the famous state space explosion problem. Because when the number of agents is too large, their interleaving actions like who goes first or who executes a task first and when would generate a lot of combinations of situations, and that leads to this state space explosion problem. So we come up with the idea of combining model checking with reinforcement learning, and we call it MCRL. So this picture shows the workflow of MCRL, which consists of 3 phases. In the first data gathering phase, we randomly simulate the model instead of exhaustively exploring the state space of the model. And since it is a time-bounded simulation, the process terminates when the simulation time ends, so the out-of-memory error is mostly avoided. Next, in the model training phase, we input these traces and their values into the Q-learning algorithm, which is a reinforcement learning algorithm, to populate a Q table, which is injected back to the original TAMA model to reform the model into a new model that is equipped with a Q table. And the Q table will be used to govern the behavior of the agent, which serves as our mission plan. So the essence of Q-learning is to accumulate the values of execution traces by this Bellman equation during the simulation process, and we store them in a Q table, which records the states of the agents and actions that are available for the agents and the values of the state and action pairs. So the next time when the agent gets to the same state, it knows better what to do next by looking up the Q table and choosing the action with the highest reward. In this way, the Q table serves as our mission plan. And this is the Q table in WUPO. It's a C-code array of data struct, and it contains Q states, Q action, and Q values. So we define the Q state as a tuple consisting of 2 elements. TP is the real valued number denoting the time point of leaving the state, and match is the tuple consisting of 5 other elements. But I don't need to read them all, you can find them in our paper. And the reason why we define the queue state as a nested tuple is because TP is only used to exclude the useless traces where agents are only um, moving but not execute any tasks. And the tuple match is used for comparison. So when the agents are searching their queue tables, they compare their current state with the elements in the match, but not with TP, as it is impossible to compare two real-valued numbers, and the elements in the match is enough to represent the state of the agent and the environment. And we define the Q action as a tuple, and the function of calculating Q values is shown in this picture. That I don't need to read them all. You can find them in our paper. And now, since we have defined all the elements in the Q table, now we can introduce some modifications that we made in order to realize this new method. So the syntactical structure of the Tama model is not changed, but we have added something into the functions of starting a task or moving to a milestone. So in these two functions, we record the current Q state, Q action, and Q value in a C-code array. And the function of finishing a task or reaching a destination do not need to record any information because they are not decided by the agent but by the environment. And in the data gathering phase, we run a simulation query to simulate the model. So the simulation query simply runs the model T times and R rounds, and the information inside this curly brackets is printed when the traces satisfies the predicate following this query. And this query is actually supported by UPO SMC, which is a branch of UPO to support statistical model checking. But in this study, we do not use this function, but only the simulation function of UPO SMC. And one thing needs to mention is that UPO SMC employs probability distribution by default in simulation. So the semantics of the original Tama model is changed a little bit. So for example, in the task execution TA, we have two kinds of time-bounded transitions. In the original Tama model, they are interpreted as arbitrary transitions, but in the UPA-SMC, they are treated as uniform distribution, probability distribution, which means that the possibility of finishing a task is equally distributed within the time interval between BCET and WCET. So this is the semantical change of time-bounded transitions. And all the channels are broadcast in UPO SMC, so they don't have to change. Now, since we have known the modification on the original Tama model, we can have a look at how the new method works concretely. So in the data gathering phase, we execute the simulation query of UPO SMC via the command line to run the model, and then we print the execution traces into some TXT files, which are used as the input of the model training phase, which is implemented as a Java program. And the program reads and parses the TXT files and runs the Q-learning algorithm to generate the Q table, which is a C-code array in UPO. So we can inject the Q table back to the original Tama model. Now, if the agent needs to make a decision, it search the Q table, and the Q table returns the action with the highest reward as the current state to the agent. So now the problem is who should do this work. So for this purpose, we design a TA model of conductors that I won't go to details of this model, but all we need to know now is that in this model, we search the Q table and returns the action with the highest reward. Then the conductor sends commands to the movement or task execution TA based on what kind of action is chosen in the make decision function. So in this way, the agent's behavior is controlled by the conductors. But how can we solve the conflict when multiple agents want to go to the same milestone? So the conductor is each of the agent is equipped with a conductor, and the conductor reads not only the Q table of its own agent, but also the Q tables of others. So it makes a comparison to know which one has the highest action and let that agent go first. So in this way, we avoid this conflict, and the agent doesn't need the agents do not need to communicate. So now, since we have gotten the new model of agents and know how to synthesize mission plans by using Q-learning, next we need to verify the synthesized mission plans against the requirements that we mentioned before. So for the first three requirements, we use invariance properties to formalize them. But for the last one, we use time-bounded least two property to formalize the event reaction requirement. And you can see that from our paper that all these requirements can be satisfied by the mission plans that are synthesized by MCLL. Now I'm going to show you the results of the experiments that we conducted to compare the performance of MCL with the original TAMA and the branch of UPO that is called UPO StratGo, which is designed to synthesize strategies to win timed games. So this branch of UPO could be possibly able to solve our problems. And by doing this experiment, we will see the advantages of MCL in scalability and usability. So this picture shows the environment model of the environment, and it is abstracted from the industrial use case that we introduced before. This table shows the tasks that should be done by the agents in this example, and some of the tasks has a fixed execution time, and some of them have uncertain execution time. This picture shows the number of explored states for checking query 8 by using TAMA and MCL. Query 8 is a reachability property that requires the agent to have one execution trace that ends at the state where all the stones are transferred and the time consumption is less than this time limit. And execution trace that witnesses the satisfaction of this reachability query can be served as the mission plan. And apparently from this picture, you can see that MCL needs much less time, much less number of explored states than what TAMA needs. And when the number of agents is 5 or 6, TAMA simply runs out of memory, as we said before. And the computation time of MCL is also much less than what is needed in TAMA. And yes, for example, the black portion means even though TAMA costs that much time when the number of agents are 5 or 6, it simply runs out of memory, whereas MCL can handle all the cases. And this picture shows the number of explored states for checking queries 6 and 9 by using UPO StratGo and MCL. Query 6 is used in MCL, which is invariance, and it requires the agent to carry all the stones within this TL time limits no matter what the execution time and movement time is. And query 9 is used in UPO StratGo to synthesize mission plan called MP that eventually carries all the stones no matter what the execution time is. So you can see the strategy here is much more comprehensive than the ones that are synthesized by TAMA, because here we use invariance and in-liveness properties to synthesize mission plans. And the number of explored states for MCL is much larger than the previous slide, but still it can handle all the cases, whereas UPO StratGo can only handle 2 agents. And the computation time for checking those 2 queries is much less in MCL than what is needed in UPO StratGo. But when the number of agents is 6, MCL needs almost an hour, and it really increases rapidly. And the reason is explained in this slide. So this picture summarizes the simulation runs that is needed to generate the Q tables and the length of the generated Q tables. So you can see the number increases rapidly along with the number of agents grows because the number of states of the model grows fast, as we showed before. So it becomes harder and harder to get to the successful traces by random simulation. And since the length of the Q tables increases, the time for searching the Q tables increases as well, which causes the verification time increases. Okay, but anyway, the result is still promising because MCL is proven to be able to synthesize mission plans for larger numbers of agents than the available numbers of what UPOStratGo and TAMA could do. And the number of task execution and movement is uncertain. So, which shows that MCL is stronger than TAMA. So, conclusion: MCL is able to synthesize mission plans for multiple autonomous agents working in an environment containing uncertainties. The synthesized mission plans are proven to satisfy various requirements. MCL is able to handle more agents than TAMA and the UPOStratGo, and the number of explored states and computation time consumed by MCL is much less than TAMA and UPOStratGo, and the number of simulation runs needed by MCL and the length of the Q table still increases rapidly. So that leads to our future work. First, rare event. So when agents have to iterate their tasks, the possibility of reaching the desired state by random simulation decreases a lot. So how can we get to the desired state in these cases without increasing the simulation runs too many is very difficult. And the reward functions of the Q learning algorithm. So the current reward function is just an algebraic formula which concerns only the execution time of tasks. So how to improve these reward functions in order to compose multiple sources of factors is very important. And last but not least, we want to synthesize and verify a controller for hybrid systems of agents since we now have the discrete mission plans already. And that's all for my presentation. If you have any questions, please contact me in this email. Thank you.